Right. Pretty straightforward.
Exactly. You can predict its path, no problem. Gravity, momentum, it all follows these nice, solid, classical rules. That's the world we experience.
But then you zoom way, way down.
Yeah, down to the level of electrons, photons, single atoms, and suddenly it feels like those rules just evaporate.
Things get weird. Really weird. Probabilistic, acting like waves sometimes, particles others.
Connected in ways that honestly just don't make intuitive sense based on our everyday experience. So the big question, the real head scratcher is, if everything is built from these fundamentally weird quantum bits, how do we get this? Our solid, predictable reality.
That's the transition we're digging into today.
Exactly. We've got a bunch of sources here, articles, research, listener notes, all tackling this quantum to classical shift. Our mission really is to unpack that, pull out the key ideas, the processes that explain how our familiar world kind of emerges from all that quantum strangeness.
And understanding just how strange those building blocks are is definitely step one.
Absolutely. The sources really lay out the peculiar nature of things like electrons and photons.
It starts with that core concept, wave-particle duality.
Right. They're not just one or the other.
Nope. The sources say they act like both. You can see an electron spread out and interfere like a wave passing through slits.
Okay.
But then, bam, it hits the detector at a single point, like a tiny particle. It seems to be both until you measure it.
Which is already pretty mind-bending. But then you add superposition. That one always gets me.
It's fundamental. Superposition means a quantum system can be in multiple states at the same time.
Like an electron in several places at once, or different energy levels.
Exactly. Multiple possibilities existing simultaneously. And that state holds until, something interacts with it like a measurement.
And it's not just location or energy. Some properties are fundamentally chunky, right? Quantization.
That's it. The sources explain these properties, like energy levels in an atom or spin, can only take on specific discrete values. No in between. They jump, they don't glide smoothly.
Okay. And then there's entanglement. Einstein's spooky action at a distance. Still sounds spooky.
Yeah, the sources definitely mention that phrase. Entanglement is this connection between two or more particles. Their fates are linked instantaneously, no matter how far apart they are.
So measuring one tells you something about the other instantly.
Instantly and definitively, yeah. It's a correlation stronger than anything classical physics allows.
And underpinning all of this, there's this inherent randomness, this probabilistic nature.
That's maybe the biggest shift from classical thinking. The sources stress that quantum mechanics doesn't give you definite outcomes before a measurement. It gives you probabilities.
Only the likelihood of finding it here, or with that energy.
Precisely. The outcome isn't fixed until you look, basically. That's when it seems to choose one state.
So, okay. The basic ingredients of reality are these probabilistic, wave-particle, superpositioned, entangled things. Why isn't everything like that? Why isn't this desk potentially also a cloud of gas until I touch it? That's the core puzzle.
And this is where the sources bring in the hero of the story, so to speak. Quantum decoherence.
Ah, decoherence, not like a switch, but a process.
Exactly. It's the main bridge the sources identify. It's about how quantum systems interact with their surroundings.
So how does that work? What's the mechanism?
It boils down to interaction with the environment. Quantum states, especially superpositions and entanglement, are incredibly delicate.
Fragile.
Very. Just bumping into an air molecule, a stray photon hitting it, even thermal vibrations. These tiny interactions constantly disturb the quantum system.
So just existing out here in the messy real world is enough to disrupt the quantum effects.
Pretty much, yeah. These interactions cause a loss of phase coherence. Think of the wave's nature. The different parts of a superposition have a specific phase relationship, like peaks and troughs lining up in a certain way. That's needed for interference effects.
Okay.
The environment acts like noise. It randomizes those phase relationships. It washes them out.
And this involves the system getting mixed up with the environment itself.
That's the next key part, entanglement with the environment. The system doesn't just get disturbed. It becomes entangled with all the particles. It interacts with the air, the photons, everything.
So the information about its original quantum state, like being in two places at once, where did that go?
It doesn't vanish. The sources explain it gets spread out, diluted across the countless particles of the environment. It's effectively lost within that massive complexity.
Lost to us, anyway. It's still there in the total system, but irretrievable for the original object.
That's a good way to put it. And the result. The system rapidly stops behaving in an obviously quantum way. No more clear interference. It looks like it's settled into one definite classical state.
Even though technically the whole system plus environment might still be quantum?
Technically, yes, the sources are clear. Quantum mechanics still applies. But the apparent behavior of the system itself becomes classical because its quantum nature is hidden, smeared out through entanglement with everything around it.
Okay, the ripple analogy from the sources makes a lot more sense now.
It's helpful, isn't it? A single clear ripple on a calm pond, that's your pure quantum state. Easy to see its form.
Right. Coherent.
But now picture a choppy pond that's the environment. Lots of complex waves. Your single ripple immediately gets mixed up, lost in the noise.
So the pattern is gone, even if the energy is still in the water somewhere.
Exactly. The distinct quantum information gets dispersed and becomes practically impossible to reconstruct.
So decoherence is like the primary driver for losing that quantum weirdness. But the sources also talk about sheer size. Scale matters too, right?
Oh, absolutely. Scale and statistics are huge factors when you go from one particle to, trillions upon trillions in everyday objects.
Like the idea of statistical averaging.
Precisely. Think about the pressure of gas in a tire. It feels smooth, constant.
Yeah.
But that pressure is the average result of billions of individual gas molecules randomly bouncing off the inside of the tire.
Yeah.
Each collision is unpredictable, quantum even. But the average of so many is incredibly stable and predictable.
It's the law of large numbers smoothing out the randomness.
That's exactly it. And this connects to the correspondence principle. Niels Bohr pointed this out.
What's the essence of that?
It basically says that as systems get larger, or their quantum numbers get very high, the predictions of quantum mechanics start to look exactly like the predictions of classical mechanics.
So classical mechanics isn't wrong, it's just what quantum mechanics looks like at our scale.
It emerges as a really, really good approximation. The sources present it that way. It works because the underlying quantum effects average out or become negligible.
Like with the de Broglie wavelength example they use for a baseball.
Right. Every moving object has a wavelength. Lambda equals h over p. Planck's constant over momentum.
But for a baseball, the momentum, mass times velocity, is huge.
Exactly. So h divided by a huge number gives you a wavelength that is astronomically tiny, way too small to ever detect.
So its wave nature is effectively irrelevant for how it moves.
Completely irrelevant in practice. That's why Newton's laws work perfectly fine for describing how a baseball flies. The classical picture is sufficient.
Okay, so decoherence scrubs away the interference through environmental entanglement, and then sheer scale and statistics make the average behavior predictable and the wave nature undetectable. Classical world emerges.
And the sources also kind of trace how this builds up, layer by layer.
Right, the complexity aspect.
Yeah. You start with quantum rules dictating atoms, electron shells, energy levels.
All quantum.
Then quantum mechanics explains how atoms bond to form molecules. Still fundamentally quantum.
It's still weird underneath.
Definitely. Then you get condensed matters, solids and liquids. Trillions of atoms interacting. Now, collective effects emerge. Conductivity, magnetism, hardness. These are macroscopic properties arising from quantum interactions.
And decoherence must be running rampant in a solid or a liquid at room temperature.
Incredibly fast. Any quantum coherence gets wiped out almost instantly, which is why a block of metal just sits there looking solidly classical.
And then macroscopic objects like our baseball or coffee cup are just enormous assemblies where decoherence and statistics rule completely.
It's a hierarchy, yeah. Quantum laws are always the foundation, but how they manifest changes dramatically with scale and complexity and interaction.
Now, even with decoherence explaining so much about why we see a classical world, the sources do point out there are still some open questions, frontiers of research.
For sure. It's not like everything is perfectly wrapped up. One big one is still the measurement problem.
Which is about...
Well, decoherence explains beautifully why a system loses its quantum fuzziness and looks classical to us due to the environment. But the sources note there's still philosophical debate about why we experience one specific outcome when a measurement happens, why this result and not another possible one.
And that's where those different interpretations of quantum mechanics come in, like Copenhagen or many worlds.
Exactly. The sources mention them: Copenhagen, many worlds, pilot wave. They offer different ways to think about what's fundamentally happening. But crucially, the sources emphasize that decoherence itself is the widely accepted physical process explaining the appearance of classicality in experiments, regardless of which interpretation you favor. It explains the transition mechanism.
And people are trying to actually see quantum effects in bigger things, right? Pushing that boundary.
Yes, that's the field of macroscopic quantum phenomena. Experiments with things like superfluids, superconductors, or tiny vibrating objects cooled way down near absolute zero.
Why so cold?
to minimize the environmental noise, the thermal vibrations, to try and keep decoherence at bay for longer in larger systems so we can study that boundary directly.
Like trying to keep the pond super still to see the quantum ripple last longer.
That's a perfect analogy. And of course, the sources briefly nod to the huge challenge of quantum gravity, uniting quantum mechanics and general relativity for extreme scenarios.
Big bang, black holes.
Right. And finally, they touch on the role of the observer.
The idea that consciousness causes collapse.
While that idea has been popular in some discussions, the sources indicate the mainstream physics view today really focuses on physical interaction. Decoherence happens because of interaction with any complex environment, whether it's a measuring device, air molecules, or, yes, even an observer. But it's the physical interaction, not consciousness itself, that's seen as the key.
So wrapping this up, the picture that emerges from all these sources is really quite profound. The classical world isn't separate, it emerges from the quantum.
That's the core conclusion, definitely. It arises through these key processes. Decoherence, hiding the quantum weirdness via environmental entanglement, statistical averaging, making large groups behave predictably, and the correspondence principle showing classical laws are just the large-scale limit of quantum laws.
So the fundamental rules don't change, it's just how they look, how they manifest, depending on the situation, scale, interaction, complexity.
Exactly. Quantum mechanics is always there, underneath everything. Its strangest features are just usually hidden from our macroscopic view by these processes.
Hopefully this deep dive gives you, our listener, a new way to look at the everyday world, to see the quantum foundation beneath the familiar surface.
It really makes you appreciate the different layers of reality.
It does. And maybe here's a final thought to chew on based on all this. If our predictable classical world is just the way quantum laws happen to look at our scale because of decoherence and statistics, what might reality be like? What might its fundamental nature appear to be at vastly different scales or under vastly different conditions where those effects play out differently, either way down low or maybe even somewhere unimaginably large?